So this is Process Dynamics and Control, Homework 2, Part C. What we have today is we're going to be deriving the time-dependent heat diffusion equation for a uniform linear bar, assuming constant thermal diffusivity. And we're going to express the heat diffusion equation from C1 as an algebraic equation via explicit differencing. And then we're going to use Colab to simulate the time-dependent response of a uniform bar, but we'll get to that here in a bit. And then we're going to use von Neumann stability analysis to explain why simulation results are unstable when R is set larger than 0.5. So that will be coming up soon. So let's start with making our bar that we're looking at. There we go. And essentially what we're going to do is we're going to take like a little snippet of it, and what we're looking at is this certain area. So this is the cross-sectional area we're looking at, which we'll call just A. And we're going to have our heat flow that goes in. We're going to have our heat flow that comes out. And to start off, what we want to look at is our net heat flow. So as usual, we're just going to go ahead and define this as Q in minus Q out. But what is the Q in minus Q out? What in terms of more detail? We're first going to look at the location. So we're going to have X as our starting point, and then we're going to have our delta X plus X as our endpoint. So that's going to be presenting that. And then I'm going to go ahead and basically plug this in as Qx minus Q delta X plus X. And we're going to leave Qx alone for a little second, but what is this in a little bit more detail? So we find that our X, once we sort of split it apart, is Qx plus dq over dx, and then the dx is just in here. So there we go. And we're just going to go ahead and plug that into our equation. So we're left with Qx plus dq over dx dx. And we're going to go ahead and cross that out as they cancel each other. So our Q net in this case is dq over dx dx. And actually, to just a little bit for the next part to make it easier to understand, we're going to actually take the Q out. And this Q is going to represent our heat flow, but what we're going to use is Fourier's law to define it. So we're going to have our Q equal to our negative K value times our change in temperature over change in location. And since we are looking at area, we're also going to go ahead and multiply this by our cross-sectional area and just plug it into that QNet equation. So we get QNet equals d over dx. Actually, I think it's supposed to be negative. Yeah, that's negative times our negative k times a dt over dx times dx. So we have our first equation pretty much set up. And what we want to do next is we want to also know what our overall flow is looking like. And this is going to basically start off with taking our density. We're going to multiply it by our heat capacity coefficient. We're going to go ahead and multiply that by our area times the change in location. And then we're also going to go ahead and use our dependent variable based off of our temperature dependent variable and it's going to be with respect to x and time, and we're just going to take our derivative of this, and since these are constants, they don't change. Oops. Except for the fact that we're going to add our dt over dx. Yep. And so now we're also going to go ahead and say that this is our next equation that we're going to be using, but I'm going to define this equation right here for dt, and we're going to utilize our equation that we found earlier. So t dx squared, and that's kind of an iteration of it, but then we're going to take this side and just do k over density times our heat capacity times our d squared t or dx squared, and this is sum to our thermal diffusivity. So our dt over dt is essentially thermal diffusivity times our derivatives. So for the next part, specifically part 2, we're going to be expressing the heat diffusion equation that we found originally, and we're going to express it as an algebraic equation using explicit differentiation. So to start off, let me do what I did in the beginning, and let's remake our diagram, and let's break it up into a few more pieces. So, and let's just go ahead and label them. So I'm going to do this one as I minus 2, I minus 1, I plus 1, and then I plus 2. So what we're doing here is, and like before, we heavily relied on looking at flow. However, this time we're going to look at temperature based off of individual sections, whereas here we just picked one and worked out the flow to get this equation. And then we're just going to basically break this up into somewhat of a matrices form and solve that. So to start, let's just go ahead and start this real quick. So we have our n plus 1 minus our ti n over our delta t, and then we're going to take our thermal diffusivity that we found right here, and we're going to break up this part into a matrices form. So what we will have is we'll have our ti minus 1 n minus r, or plus 1 minus ti n over delta x minus our t I n minus our ti minus 1 n over delta x, and we're going to divide that all by delta x, and then we're going to go ahead and simplify this. So what we end up getting is plus 1n minus 2 ti n minus ti minus 1 n over delta x squared. So from here, what we're going to do is we're just going to try and get our ti n plus 1 value alone. That's what we're going to be looking for. So we're going to have ti n plus 1 minus ti n, and then we're going to move our delta t over. So then we'll have our thermal diffusivity multiplied by the delta t, which is time, over our delta x squared, and then go ahead and have our ti plus 1 n minus 2 ti n minus our ti minus 1 n, and then we're just going to move our tin over, so we get our tin plus 1 value or variable separated. Just have tin plus that entire expression all over again, minus 2 tin minus ti1. And there we go. So that is our heat diffusion equation turned algebraic. And this is in terms of temperature. And now we're going to go ahead and simulate that time-dependent response of a uniform bar. And we're going to do that in Colab. This is the coding section. We're opened up in Colab now. So I already have my library and our print options set up. So what we're going to do now is we're going to simulate this, and we're going to start with our R value, which it's supposed to have it in the problem statement, but it didn't copy over. But basically this is our, it's a little easier to write with a pen, but this is our R value, and we're just going to basically just express that as a derivative. Alpha times R dt divided by dx squared. So there's our R, and as shown in our problem statement, we're going to have our R equal to 0.499, 0.5, and 0.501 to see their comparison. So we'll start with 0.499 and shift enter. And as we see, we're going to be distributing this bar into 50 sections, so we're going to have n equals to 50. And then our temperature is going to be set to np.full n20. And then we're going to be raising it to 40 and 100 degrees Celsius. So actually this is 40. And then our T-1 will be 100. And then we're going to get right into making our subplots, essentially. Underscore subplots, and then fig dot add underscore scatter. Yep. X equals okay, actually I knew I was missing something, so we're gonna have IDX equal to np dot arrange at n, and that's what our x is equal to, and then our y is just our temperature, and then we're going to have mode equal to lines, and then our name is initial t. Yep, there we go. So next here we're gonna make a for loop. So for n in range, we're gonna set to 5,000. Now we're gonna basically rewrite our algebraic expression that we found before, except in code. So which equals, just gonna repeat this, plus our R value, which we've already defined, times So we have our minus our 2 times our it should be 2 times t, which is 1, give 1, and then close that off. Should be good. And then we're going to put in a if loop, basically saying that if we take n divided by 50 and it comes out to 0, we're going to utilize this line of code, and we're going to set that as a fake underscore scatter idx, and yep, AI pretty much got it there. So it's going to just take instead it's going to use this line of code rather than this if n divided by 50 is equal to 0. So let's just see if that works. Okay, I did encounter a little error. So a few things that we fixed. So the 20, we needed this period to, I guess, define it as an integer, and without it, it just wasn't giving me a proper graph. And then we also changed this to negative and or addition, and then we changed this from a 1 to 2, as that's kind of what our equation states. So runs perfectly now. And using the 0.499 value, we can see that our tube is nearing steady state, or is at steady state, and initially it's pretty flat, and then as time goes on and iterations, it reaches that linear heat diffusion line that we're looking for. But we are given 2 more values, so let's see what happens when we change it to 0.5. Okay, so it's about the same, and then we change it here. Yes, so it kind of goes a little wacky, so I guess our cutoff point would be 0.5. Okay, so for the fourth part of this homework, we're going to be using the von Neumann stability analysis to basically explain why we saw that instability after 0.5 when we were doing the coding. So this is going to help clear that up. So first I already have the equation that we need that we found before, which is dt over dt equals the alpha times d squared times t over dx squared. And then we're going to find temperature, and we're just going to rewrite this equation basically in terms of exponentials. So we have kx times our e times our negative alpha k squared times temperature. This gives us our temperature, and then we're going to write 2 more derivations. So the first one is the change in temperature with respect to time, which is just basically this right here. So alpha times k squared is temperature. And then we're going to have change in temperature based off of location, which is just IKT. So next, after this, we want to look at our temperature once again, except this time we're going to be looking at the summation of it. So we're going to take our CK value times IKX, and then this is multiplied by our k squared times t, and then basically we're just gonna sum this up to basically the same thing. Okay, so we'll also go ahead and define our d squared t dx squared as negative k squared times t. Oops. Okay, there we go. And now what we're going to do is we're going to take this equation right here and we're going to tune it to fit our, I guess, location-wise on our tube. So how we did in I minus 2, I minus 1 to account for that, we're going to do the same thing with j, but use this equation. So how that looks like is we'll have I times k times j times r delta x, and then multiply this by negative alpha times k squared times n times r delta t. And then if we take j plus 1 and then n, we can see that this equation becomes j plus 1 times square delta x times our e times, and then it's just going to be the same thing for here since we didn't really change anything with n. And then we're going to simplify this equation down, and we can see that tjn is pretty much the same right here. So if we were to smooth this out, you get e to the ix times delta x times our tjn. And since we found tj plus 1, we'll go ahead and do tj minus 1n. And it's basically the same thing, except we're going to have a negative sign in front of our I, and we'll have tj. And now what we'll do is recalling our equation that we used in our code that utilizes our r. We're just going to do the same thing here, except apply what we know. So plus r, and we'll take our tjn out just for the sake of ease. I have our ik delta x minus 2 plus our e times ik delta x. There we go. And then we can simplify this to and 1 plus our r times 2 cosine k delta x, and then should be minus 2. I have to double check that, but yep, that should be correct. Okay, so just want to point one thing out. So I had to take out this parentheses because it isolated this, and minus 2 is supposed to be a part of this. So that's taken care of. But our next step is we're going to take our absolute value and we're just going to take this entire expression within the parentheses. And we're going to go ahead and write it down. Just 2. And we're going to set boundaries for it, so it can't be greater than 1, and then negative 1. And we're going to move our 1 to both sides and subtract it, so we're left with negative 2 less than or equal to r times 0. So after this, simplifying it further and solving it out, you're going to be left with 1 is greater than or equal to 2r, which you'll end up getting r is less than or equal to 1/2, which explains as to why 0.501 in our code caused our graph to go unstable. It's because mathematically speaking, it should be under or it should be 0.5.